Hi everyone, welcome back to Chem Story. Today we're diving into another key reaction of alkenes, oxymercuration, demercuration. This reaction adds water across a double bond, just like acid-catalyzed hydration. But here's what makes it interesting. You get Markovnikov addition without forming a carbocation ion and without any rearrangement. That's a big deal when you want to avoid messy side products. So let's take it step by step and see exactly how this reaction works. So here's the big idea. We're taking an alkene and turning it into an alcohol using mercury acetate. This is a hydration reaction that follows the Markovnikov rule. That means the OH group ends up on the more substituted carbon. But unlike acid-catalyzed hydration, this one follows a different path. There's no carbocation ion involved. Instead, it forms a bridged mercury intermediate, and that's what leads to anti-addition. So in the end, you get an alcohol where the OH and the H add to opposite sides of the double bond. And that's exactly what we're going to break down next when we look at the mechanism. Now let's take a quick look at the overall mechanism. There are 4 main steps to keep in mind. First, mercury acetate slightly dissociates in solution. That gives us an electrophilic mercury species. Then in step 1, the alkene attacks that mercury, and we get a bridged mercurinium ion. In step 2, water comes in from the opposite side, which leads to anti-addition. We'll go through each step in more detail in just a bit. But for now, just focus on getting the big picture. Then, in step 3, we lose a proton, and that gives us a neutral organomercury alcohol. And in step 4, we move on to demercuration. We treat the compound with sodium borohydride, which swaps the carbon-mercury bond for a carbon-hydrogen bond. So by the end of all this, the mercury is completely gone, and what we're left with is the final alcohol product. Alright, let's walk through the mechanism step by step using this example. We start with an alkene, and we add mercury acetate in the presence of water. In solution, mercury acetate dissociates just a little, and that gives us a positively charged mercury species. The double bond is electron-rich, so it acts like a nucleophile and attacks the mercury. At the same time, the mercury connects to both carbons of the double bond, forming this 3-membered ring called a mercurinium ion. And this part is key. It's not a carbocation ion intermediate. That means there's no free rotation and no rearrangement. In the next step, water comes in and attacks the more substituted carbon, but it has to approach from the front side because the back is blocked by the mercury bridge. And here's why it goes for the more substituted carbon. Even though there's no full carbocation ion, the bond between mercury and that carbon is a little weaker, so that carbon carries more partial positive charge. That makes it more electrophilic, so the water is more likely to attack that side. That's why we get anti-addition. Then in step 3, the water that just added loses a proton, and we're left with a neutral organomercury intermediate. Finally, in step 4, we treat it with sodium borohydride, and that replaces the mercury with a hydrogen. You don't need to worry about the exact mechanism for this step. We usually just treat it as a clean substitution and move on. And just like that, we get our final alcohol. That's the full oxymercuration-demercuration mechanism. Let's talk about regiospecificity, or in other words, where each group adds during this reaction. This one follows the Markovnikov rule, so the OH group ends up on the more substituted carbon, and the mercury group goes to the less substituted one. In the final step, during demercuration, it gets swapped out for a hydrogen atom. So in the end, what you're left with is OH on the more substituted carbon and H on the other. Now let's look at stereochemistry. In other words, how the groups add in 3 dimensions. This reaction gives anti-addition. That means the OH and the H end up on opposite faces of the double bond. And that actually makes perfect sense when you think about the mechanism. The water attacks from the front side of the alkene because the back is blocked by the mercury bridge. So the 2 groups can't add from the same side, and that's why the final product always shows anti-stereochemistry. So why would you use this reaction instead of simple acid-catalyzed hydration? Well, here are a few clear advantages. First, the yield is usually higher. You're not dealing with an equilibrium like you are in acid-catalyzed reactions, so the reaction goes more cleanly to completion. Second, there's no rearrangement. Since there's no carbocation ion involved, you don't have to worry about things like hydride shifts messing up your product. And third, the reaction happens under mild conditions. You don't need heat or strong acid to get it to work. But of course, it's not perfect. There is one big downside. This reaction produces elemental mercury, and that's highly toxic. So safety becomes a serious concern if you're planning to use this method in the lab. There's also a really useful variation of this reaction. It's called Oxymercuration Demercuration. It works almost the same way as the reaction we just saw, but instead of water, you use an alcohol, like methanol or ethanol. So instead of making an alcohol, you end up making an ether. Everything else stays the same. The mechanism, the regioselectivity, and the stereochemistry all follow the same pattern. So this is a great way to make Markovnikov ethers, starting from alkenes. Here's what that looks like in the mechanism. Just like before, the alkene reacts with mercury acetate to form a bridged mercurinium ion. Then, instead of water, the alcohol acts as the nucleophile. It attacks the more substituted carbon from the front side, because the back is blocked by the mercury bridge. That gives us an organomercury intermediate with an OR group attached. After deprotonation, and then treatment with sodium borohydride, the mercury is replaced with a hydrogen. And just like that, we're left with an ether. So again, this is Markovnikov addition with anti-stereochemistry, but now we get an OR group instead of OH, and that wraps up the full picture for oxymercuration and its variation. All right, so that's it for today's lesson on oxymercuration demercuration. Hope this helped you see not just how the reaction works, but also why it's useful and when to use it. Thanks so much for watching, and I'll see you in the next Chem Story video.